Okay, so we have been discussing the radiative corrections. What we have seen is in the at the one loop level, these three diagrams are relevant. This is one, and then we have this diagram. Finally, we have a diagram like this, where there is a fermion loop in between. We have discussed the contribution of this diagram in great length, and then we saw that this actually in fact gives correction to the vertex function. The vertex function, using symmetry argument and word identity, you can express it in terms of the form factors, and what this diagram does is that it actually gives one loop contribution to the form factors. And in the last few lectures, we have computed the one loop contribution to the form factors by evaluating the contribution from this diagram explicitly. In the next few lectures, we will discuss these two diagrams in great detail. This diagram especially gives the self energy. This is called as the electron self energy diagram, and this is called as the photon self energy or the vacuum polarization diagram. This diagram contributes to the electron self energy. We will first discuss the contribution of this diagram in detail, and then we will come back to this diagram. So the 2-point function, we know already at tree level, it is basically given by this diagram here, and the contribution here is basically it is just the free propagator. If I denote this to be P, then the propagator here is given by I P slash plus m 0 divided by P square minus m 0 square plus I epsilon. Basically, you consider this in between some external lines. For example, if you have a process like this, something like that, the propagator part is given by this. This is at the tree level, and at the one loop level, this is what is the diagram. So this the electron self energy at one loop is given by this diagram here. I will call this to be P, and this is again P. If I denote this to be K, this will simply be P minus K, and this will be the next order contribution to the propagator, and so this is just again, when I write this, I do not care about the external lines, just like here. In this lecture, we will focus basically on this diagram, and then we will evaluate it in explicit in great detail. We can use the Feynman rule, and the amplitude, the contribution from this diagram is given by this. I will first write down the formula, and then I will explain it in detail. So basically, this is, there are two propagators here, and then there is this loop here, which contains one fermion propagator, one photon propagator. So we have to write all these propagators and then these vertex functions here, and then because there is a loop here, we have to integrate the loop variable k. That is what is basically given here. And also I must say that I have now used m 0 to be the mass of electron. You will see at the end of this lecture why I have denoted it as m 0 instead of m, because in all our previous lectures we used the notation m for electron mass. Basically, that's the reason it's called as self energy. It will give this diagram will give the correction to the mass of the electron. It will shift the mass of the electron, and that's what we will see when we do the explicit computation. So this diagram gives this vector here I p slash plus m 0 divided by p square minus m 0 square, then minus I sigma 2 of p I p slash plus m 0 divided by p square minus m 0 square, where minus I sigma 2 of p is given by minus I square integration gamma mu I k slash plus m 0 divided by k square minus m 0 square plus I epsilon gamma mu minus I divided by p minus k square minus mu square plus I epsilon. So to explain it in detail, this is the electron self energy diagram here. This is P, and this the fermion propagator here. The contribution from this propagator is given by this term here, I p slash plus m 0 divided by p square minus m square, and here this is the this loop here, which I denote to be minus I sigma 2 of p. 2 here because it is as you can see it is E square, because of that it is 2, or it is because it is one loop contribution, that is why this symbol 2 here is. And then there is this fermion propagator here, which is again given by I p slash plus m 0 divided by p square minus m square. This I sigma 2 is the contribution from this loop. As you can see that for these two vertex you have minus I e gamma mu for this and another minus I e gamma mu for this. Then the fermion propagator here is given by this is k. So therefore this is the contribution here is given by I k slash plus m 0 divided by k square minus m 0 square, and then this vertex here, this gamma mu minus I e here, and this photon propagator, which is p minus k, is the momentum carried by this photon, virtual photon here, and this the contribution here is given by minus I over p minus k square. And because there is a loop, we have to integrate over the loop variable, which is d 4 k over 2 pi to the power 4th. Note that this diagram has also an infrared divergence. At this point, we are not interested to study the infrared divergence. What I have done is to cure this infrared divergence, I have put a cutoff to the photon mass here, that is given by this mu square. So there is a small photon mass I have given, so that there is no infrared divergence. So if we have time, we will discuss the infrared divergences in these processes in more detail, but at this moment we will just put a regulator and we will evaluate this this diagram here. All right. So again, we know we have evaluated the diagrams like this, integration like this, when we discussed the vortex correction. What we need to do is we need to use the Feynman parameterization. So you have already seen this formula earlier, 1 over a b can be written as a integration 0 to 1 dx 1 divided by x a plus 1 minus x b whole square. Here these two factors are a and b. So, what I will do is that I am interested in writing this quantity 1 over k square minus m 0 square plus I epsilon times p minus k whole square minus mu square plus I epsilon in this form here. So, this is given by integration 0 to 1 dx 1 divided by k square minus 2 x k dot p plus x p square minus x mu square 1 minus x m 0 square plus I epsilon, this whole square, because there is a square here. If I substitute this for a and b, then it is just straightforward to see that this is what you will get in the denominator. So, what I want is I would like to again complete this square here. There is a quadratic term in k and there is a term which is linear in k. So, what I will do is that I will observe this term here and I will write it as a complete square, so that we can do the d4k integration. Remember, this k is the loop variable and then we have to integrate over this over all values of k, and to do the integration I need to complete this square here. So, what I will do is I just consider this term here, for example, k square minus 2 x k plus 2 x k dot p. So, to observe this linear piece, I introduce this variable L, which is k minus x p. Then I can write the denominator in terms of L square and so on. So, in terms of, instead of writing this in terms of the variable k, if I write it in terms of the variable L, if I use the variable L, then what I will get in the denominator is the following. This denominator here can be written as 1 over L square, whatever is left I will denote that to be delta. So, 1 over L square minus delta plus I epsilon, which is there, this whole square. So, you can see that if you use L equal to k minus x p, then this delta will be given by delta is equal to minus x times 1 minus x p square plus x mu square plus 1 minus x m 0 square. This is what is the expression for delta. So, this is what is the denominator here, and this. So, if we come back to this diagram, what we have done is that we have used Feynman parameterization to write this, and the denominator here is basically given by integration 1 over or dx, where x goes to 0 to 1, L square minus delta plus I epsilon whole square. What about the numerator? The numerator is given by this. So, there is a minus I e square and there is a I here, and what we are left with is gamma mu k slash plus m 0 gamma mu. So, this is what is the denominator part, and the numerator is given by minus I e square minus I here gamma mu k slash plus m 0 gamma mu. We can simplify this, it is utterly straightforward, and you can see that you will get there is another minus I here. So, what I have is minus I square. So, totally you get minus E square and gamma mu. We have used the definition L equal to k minus x p, therefore, k equal to L plus x p. Since we are using instead of k, we are using the variable L as the integration variable. So, I have to express this in terms of the variable L, and so this is simply given by L slash plus x p slash plus m 0 gamma mu. But now, the denominator has only L square, and L takes all values from minus infinity to plus infinity. Therefore, the term which is linear in L in the numerator will be actually an odd function of L, and when it is integrated for all values L, it will give you 0 contribution. So, the linear terms in L will simply go away when we perform the L integration here. So, therefore, the numerator what we are left with is it is simply minus E square gamma mu x plus x p slash plus m 0 gamma mu. This is what we are left with, and this you can see if you take the gamma mu inside, gamma mu will give you 4 here. So, you have 4 m 0, and gamma mu p slash gamma mu we have evaluated it any number of time, it is simply given by minus 2 p slash. So, at the end of the day, this numerator here is simply given by minus E square minus 2 x p slash plus 4 m. So, we will substitute this for the numerator. Here L should be the integration variable, and this is what for the denominator, and at the end of the day when we substitute all these things, what we will get for I sigma 2 is it is simply given by minus I sigma 2 of p is equal to minus E square 0 to 1 dx, and then also integration over d 4 L divided by 2 pi to the power 4th. Then in the numerator we got minus 2 x p slash plus 4 m 0, and in the denominator we have L square minus delta plus I epsilon square. This is what we have for the from the loop. Now, you can just do the power counting here, and then you can see that this L integration is actually divergent. In fact, it is logarithmically divergent. So, what you need to do is you need to introduce a cutoff. We have already done it when I discussed the vertex function. So, what we need to do is here we will just use the Pauli-Villard regularization. So, we will put an upper cutoff to the momentum k. So, the cutoff, the ultraviolet cutoff UV cutoff is denoted by lambda. So, we will integrate the instead of taking the all values of k, we will take the integration variable k from only up to the value lambda. So, this is what so this amounts to replacing this photon propagator here. simply by so in the Pauli-Villar's regularization, you introduce a UV cutoff to the momentum to the photon momentum, and that simply amounts to replacing this photon propagator minus I divided by p minus k whole square minus mu square plus I epsilon by minus I divided by p minus k whole square minus mu square plus I epsilon minus I divided by p minus k whole square minus lambda square plus I epsilon, where this lambda is the UV cutoff. Ultimately, we would like to take the limit lambda goes to infinity. So, this is what we will do. Instead of this, we will substitute this. So, then in I sigma 2, you will basically have two terms. One term is given by this, the other term will look exactly like this, except that instead of mu, you will have this capital lambda. All right. So, what you will have here is again everything will be exactly as it is, but instead of 1 over L square minus delta whole square, what you will have is 1 over L square minus delta whole square minus 1 over L square minus delta lambda. I will denote whatever the quantity to be delta lambda. So, this is what you will get. Instead of this, the effect of the UV cutoff will be to introduce another term here 1 over L square minus delta lambda. We already know the expression for delta here. Delta is given by minus x into 1 minus x p square plus x mu square plus 1 minus x m 0 square. This is what is our delta. Therefore, delta lambda, the effect of the UV cutoff is just to introduce another term where this mu is replaced by lambda. So, delta lambda is merely given by this, where this mu square is substituted by lambda square, and this quantity ultimately we will be interested in the limit lambda goes to infinity. Therefore, in the lambda goes to infinity limit, this is merely given by x lambda square. So, so in place of delta lambda, we will simply use x lambda square. So, this is what we will be interested in evaluating, and so we have again we have evaluated similar integrations when we discussed the vertex correction. So, I will briefly summarize the result. What you have is this integration d4 L divided by 2 pi to the power 4th 1 over L square minus delta whole square. I will weak rotate this. So, what I will do is that instead of L 0, I will just write it as L E 0, which I will denote as minus I L 0, and then I will do the integration in the Euclidean space. So, this and the regularization, the introduction of UV cutoff together will amount to replacing this integration here by I divided by 4 pi whole square. Remember, I will introduce this, and also I will integrate over the angular variables. The angular variable integration will give me a 2 pi square. So, this 2 pi square will simply cancel this 2 pi to the power 4th, and what I will be left with is 4 pi square here. This I is because of the Euclidean continuation, and finally, what I will be left with is an integration over d L e square. L e square is my integration variable divided by L e square divided by L e square plus delta whole square minus L e square divided by L e square plus delta lambda whole square. This is what I have at the end of the day, and you can see that when you perform this integration here, you will get a finite piece. I will not be interested in the finite piece, plus you will get a term which is logarithmically divergent. For example, you can write it as L e square plus delta lambda minus delta lambda. The first term will give you 1 over L e square plus delta lambda. When you integrate it over, so this integration goes from 0 to infinity here. L e square takes values from 0 to infinity, and this here will have a finite piece term plus 1 over L e square plus delta lambda, and when you integrate it, you will get log L e square plus delta lambda, and similarly here you will get a log L e square plus delta. Finally, when you evaluate it from 0 to infinity, you will simply get log delta lambda divided by delta with a factor I over 4 pi whole square. So, finally, when you evaluate this integration, this is what you will get here, and so this is only the L integration, and then you have the x integration here. So, what I will do is that if I substitute whatever we have evaluated earlier, if I substitute for that, then I will get for minus I sigma 2 of p, this minus e square and 4 pi will give me alpha divided by 2 pi. Finally, this I also I will observe here. So, this is simply given by 0 to 1 dx, and in the numerator I have if I just cancel this 2 here, 2 m 0 minus x p, x times p slash, and finally log delta lambda divided by delta. Delta lambda we already know is given by x capital lambda square divided by 1 minus x m 0 square plus x mu square minus x 1 minus x p square. This is what you get for sigma 2. You can see, so we will discuss what does it mean physically little later, but you can see already that this because of this log here, it has actually a branch cut, and for any value of branch cut, the branch cut starts when the denominator there is a branch cut whenever the denominator is negative for any value of x, and it starts when this quantity becomes 0. So, for any x, the branch cut starts when this quantity 1 minus x, when the denominator simply vanishes, m 0 square equal to 0 plus x mu square minus x into 1 minus x p square, this equal to 0. Okay. So, you can solve for it, and then you can see you can see that this quantity is negative for sufficiently large p. So, for any p, if you have a real solution for x, if this equation admits a real solution for x which lies between 0 to 1, then you have a branch cut. And you can solve it for you can solve this equation, and of course, this is a quadratic equation in x, and the solution is utterly trivial. It will be given by x equal to half plus m 0 square minus mu square divided by 2 p square plus or minus k. I will not define this k here, but you can get it by solving this equation, and this k is precisely the momentum if you evaluate the threshold momentum for creation of two particles, then this will be given in the center of mass frame. This is given by this k here. Okay. All right. So these are basically the analytical behavior of this expression here, and then about the branch cut. What we will do now is we will see what can we tell about the exact propagator. So what we will do is that we will introduce of course, this is at one loop level, but at two loop level, what can you expect? You can have a diagram like this, or you can have a diagram like this. At three loop level, you will have diagrams like this, and so on. However, you can see if you look at this diagram or this diagram, if you cut here, then this diagram is divided into two separate pieces, two one loop diagrams. Whereas here, if you remove any internal line, you cannot separate it into two separate diagrams. So, for example, if you cut here or here or here, wherever you want to cut, you cannot simply separate it into two diagrams. Therefore, these diagrams like this are known as one particle irreducible diagrams, whereas these are not irreducible diagrams, these are reducible. So these ones we will denote to be 1 pi, one particle irreducible diagram, and at the lowest order at one loop level, which is order E square, it is simply given by minus I sigma 2. To all orders, I will denote these one particle irreducible diagrams to be by this simple, well, I will write 1 pi for one particle irreducible. This is the one particle irreducible diagram to all orders, and these will be given by summing over all one particle irreducible diagrams. So, you have diagram like this is at 2 loop, plus you have another diagram at 2 loop, which is given by this, then you will have 3 loop, and so on. All such diagrams you sum over, and this is what you have. If this is what you denote as the one particle irreducible diagram, then the exact propagator basically will be given by sum which involves all such one particle irreducible diagrams. So this so the 2-point function to all orders, I will basically denote it like this, and this will be at tree level. Of course, this is just the free propagator. At then you have contribution from this, then you have and so on. Sum over all such terms are will basically give you the exact propagator. This I will denote to be minus I sigma of p, and we would like to evaluate the exact propagator here. So the exact propagator basically will have the following form. So the tree level part, of course, we all know. To write it again, you have this is given by this plus and so on. This quantity here is merely given by I over p slash plus m 0 divided by p square minus m 0 square, whereas this quantity here, you remember this, I am denoting this quantity to be minus I sigma p without these two propagators here. So, if I include these two propagator also, what I have is for this propagator here minus I or I p slash plus m 0 divided by p square minus m 0 square, and then this one I am denoting it to be minus I sigma, and again here I p slash plus m 0 divided by p square minus m 0 square, so on. So, this is the contribution from this term. Similarly, you can write down the contribution from this term, which will involve one such one fermion propagator here, then minus I sigma for this, another fermion propagator minus I sigma, another fermion propagator, and so on. So, this you can write it like this. You can see that this the tree level term has actually it has a single pole at p square equal to m 0 square. This term has a double pole at p square equal to m 0 square, because it is 1 over, this term contains 1 over p square minus m 0 square whole square. Similarly, this will have a triple pole and so on. So you will have all this diagram, the full propagator will involve higher order poles of all powers. This looks worse, but it is not as bad as it looks, because you can, as you can see, it has a geometric series which you can sum up exactly. Because you can sum up exactly, it basically what at the end of the day what we will get is basically a simple pole which is shifted. Instead of getting the pole at p square equal to m 0 square, we will see that we will have a simple pole which is shifted. So, let let us sum it up and then see what we get. It's of course, it's very straightforward to sum it up. I will rewrite this term here. I will simply write it as I, the first term is I p slash minus m 0, and the second term here is basically I divided by p slash minus m 0 times I sigma so this minus I will give you plus 1. So, sigma of p divided by p slash minus m 0, and the next term will again will be exactly like this. You will have I p slash minus m 0, and this quantity will appear twice. So, you will have sigma of p divided by p slash minus m 0 whole square, and so on. So, this you can of course write it as I divided by p slash minus m 0 times 1 plus sigma p over p slash minus m 0 plus sigma p over p slash minus m 0 whole square, and so on. You can see this is a geometric series, you can sum it up exactly, and when you do, at the end of the day what you get is this times 1 over 1 minus sigma of p divided by p slash minus m 0. So, you can take it inside in the denominator and you can multiply, and what you have is simply 1 over p slash minus m 0 minus sigma of p slash. So, everything will involve p slash only. This is what you will get. So, you can see at the lowest order it looks like there is a pole at p slash, the propagator has a pole at p slash equal to m 0, but when you consider the exact propagator, this is what is the expression for the exact propagator, and the exact propagator has a pole which is not located at p slash equal to m 0, but the location of the pole is shifted. It is simply a simple pole and it is actually shifted. It's shifted to the point when the denominator is 0. So basically the simple pole is when p slash minus m 0 minus I sigma of p equal to 0, sigma of p slash equal to 0. We will denote the location to be m. So, p slash equal to m, the solution of this equation we will denote to be m. So, therefore, this equal to 0 when p slash equal to m, and then we see that this m, which is actually the physical mass, is not exactly equal to m 0. M 0 is known as the bare mass and m is the physical mass, and the physical mass is basically determined by the simple pole of the exact propagator, and we can compute this m if we know what sigma p is, and we know sigma p order by order. We have just now computed sigma p to the second order in E. So, therefore, we have an expression for m in terms of m 0 and so on. So, that is what we will denote. So, this is simply p slash equal to m. If I say delta m to be the difference between m and m 0, so this is basically m minus m 0, and delta m is what we have computed, and this is given by sigma 2 at p slash equal to m. To the lowest order we can write it as sigma 2 evaluated at p slash equal to m 0. So, we have already evaluated sigma 2, and if we simply substitute p slash equal to m 0 or p square equal to m 0 square, then what we will get is basically given by delta m equal to alpha divided by 2 pi m 0 integration from 0 to 1 dx 2 minus x log x lambda square divided by 1 minus x whole square m 0 square plus x mu square. So, therefore, this diagram here actually, so what we have got is sigma 2 comes from this diagram here, and it basically gives mass shift for the electron. This diagram contributes to the mass of the electron, and it's basically the shift in the mass of the electron is given by this diagram here. And you can see with this that we have already discussed this diagram is actually divergent. You can see it because of the presence of lambda square. We had introduced a UV cutoff here, and ultimately we would like to take this cutoff to infinity. And when you take lambda goes to infinity, this diagram this term here is actually divergent. So, you have a logarithmic divergent here. Therefore, it looks like the shift in mass is actually divergent, and you can say that the perturbation theory does not make sense, because you are doing a perturbative expansion, and then the next order term is basically divergent. Well, at this point, although it looks like it does not make sense, it is because we have started with m 0 in the Lagrangian. When we did the QED Lagrangian, we started with had m 0 as the mass of the electron, and this m 0 itself is divergent. That is why this term here looks like divergent. Instead of this, so this m 0 is known as the bare mass, and this computation tells us that the bare mass is not a finite quantity, it is a divergent quantity. What is finite is the physical mass. The physical mass of the electron is not divergent, it's a finite quantity. So, what you need to do is you need to renormalize the mass of the electron. Instead of so what you need to do is that you need to modify the Lagrangian, the QED Lagrangian you started with appropriately, so that it contains finite quantities. If this Lagrangian contains finite quantities, then the perturbation theory will of course make perfect sense, and therefore, so by renormalizing, what you do is that you observe the divergence in the bare mass, and ultimately what you get is a finite quantity, and if you do the perturbation theory in terms of this finite quantity, then everything makes perfect sense. So what we did here is we have discussed the electron self energy term in great detail. What we will do in the next lecture is we will compute the photon self energy term, which is given by this diagram in a similar manner, and then we will see what this term basically gives. Okay.